So good morning students, this is Dr. Anwar from Department of Science and Humanities. So I am back with a new session of engineering chemistry. So in this session I will be talking about the basic chemical bonding, and this chemical bonding is very important for any of the engineering students, and this has led to the modern theories of molecular orbital theory, crystal field theory, and any other new theories actually which we are going to come in the further sessions. So here we go. So coming to the contents, I will be talking about the introduction of chemical bonding. Then I will be going to talk about the Lewis structures, which was laid by Lewis and Kossel. And finally, I will be talking about the VSEPR theory, that is the valence shell electron pair repulsion theory, which we have undertaken in the 10+2 level. And we will be talking about the VBT, that is the valence bond theory. Starting from the first topic, that is the introduction. But before that, let me talk about the aim of this video lecture. So I will be telling you about what is the basic meaning of a chemical bond, and from this video lecture we will try to understand the primitive theories, that is the Lewis theory, the VSEPR theory, and the valence bond theory, which were the basic theories to understand the structure of any of the chemical compound. Before I start this the basic chemistry bonding, so let me talk about the chemistry of life. Ego is a breaking bond which breaks the chemical bond called as the friendship. So with this quote, let me start this chemical bonding chapter. So what is this chemical bonding? It refers to the formation of a chemical bond between two entities. Okay, so where the attractive forces they hold the constants and they stabilize with the loss of energy. So whenever we try to make a bond, definitely there should be some loss of energy. So with this, we will try to understand the basic chemical bonding. Let us come to the basic ionic bond. In an ionic bond, we have got a Coulombic attraction between a positive and the negative charge species. And this attraction is non-directional because the strength of the interaction between depends on the distance. Okay. So more the distance, more is the strength of the ionic bond. Less the distance, less is the strength of the ionic bond. And this ionic bond is cleaved whenever you try to dissolve the substance in a polar solvent. Polar solvents such as water, ethanol, methanol, any other alcoholic solvents. Let us try to take this example. We have got an ionic bond between a sodium fluoride. We know that sodium is having an atomic number of 11 with a configuration of 2, 8, 1. With fluorine, atomic number 9 and configuration of 2 and 7. So this fluorine atom has to get one electron to get this octet. So we are very familiar with this term octet, where any atom tries to attain 8 electrons to get stability. Since this sodium atom has got one electron, it doesn't actually require this electron to maintain the octet. It has already got the inert configuration of 8 electron rule. So on transferring this one electron to fluorine, this sodium is helping the fluorine atom to gain octet. So in an ionic bond, we have got a transfer of electron from a most electron positive atom to a electronegative atom. So this actually will create a charge of a plus and a minus, and this actually a Coulombic attraction actually is present between two entities, okay, in a ionic bond. Let us go to the next one. In a covalent bond, we have got a mutual sharing between two entities, and this bond is formed between two or more non-metals having difference in the electronegativity, and we should be very clear that the electronegativity difference actually should not be very high, because more the difference in the electronegativity, more it is difficult to form a covalent bond. So we've got a bond actually between two electrons, and these two electrons actually are the one actually which are sharing. Okay, so they satisfy the octet rule by sharing of electrons. And let us try to start about actually this simple molecule, that is hydrogen. In hydrogen we have got one electron, and another hydrogen atom has got one electron. This hydrogen atom can attain stability by having two electrons. So even this hydrogen atom, it attains stability by having two electrons. So they try to mutually share the electrons, and by coming together, and they try to form a covalent bond with the loss of energy. So whenever actually, I again want to repeat this one, whenever we try to make a bond, whether an ionic bond or a covalent bond, we try to lose some amount of energy. And these molecules, they have got a definite shape. Let us work on actually with the third class of bond, that is the coordinate covalent bond. In a coordinate covalent bond, we have got two electrons coming from the same atom. And this coordinate covalent bond or a dative bond is generally represented by a arrow coming from a atom or a molecule which is having excess or surplus of electrons. And it is these two electrons which are involved in the bond formation. So whenever I talk about an ionic bond, in an ionic bond, one electron is coming from an electropositive atom, the other electronegative atom will try to gain the electron. In a covalent bond, we have got two electrons shared between two atoms which are having a similar electronegativity. In a coordinate covalent bond, we have got a pair of electrons coming from the same atom or a molecule. So in this case, we have got a ammonia molecule, and this ammonia molecule has got a lone pair of electrons on nitrogen atom. And we have got another actually entity, that is the BF3, which is a Lewis acid. And this Lewis acid is electron deficient in nature. It requires two electrons to get the stability of octet. So these two electrons are coming from the nitrogen atom. So this is the way we can say that a coordinate covalent bond is formed between an ammonia and a BF3. Similar kind of coordinate covalent bond is formed between an ammonia and a silver ion. So this kind of coordinate covalent bond is a two-centered two-electron bond where we have got two electrons coming from the same atom or a molecule. So this is where we are going to classify the ionic bond, a covalent bond, and a coordinate covalent bond. All these bond formation, they are accompanied by loss of energy. Let us go to the first theory, that is the Lewis structures. It was Kosel and Lewis actually who started actually this dot-like structures, and this was the primitive periodic table where the hydrogen atom was represented by a single dot. That means it has got one electron in the outermost shell. The helium, it is represented by He with two dots. So in this Lewis-Kosel approach, we are trying to represent elements based on the valence electrons. Let us come to lithium. Lithium atomic number being 3, but it has got only one electron in the outermost shell. I can write or represent actually as Li dot. The same case with beryllium. In beryllium, though the atomic number is 4, I have got 2 electrons in the outermost shell, so I am trying to represent Be 1 dot and the second one. The same case it was followed for the chlorine atom. In chlorine atom, since the atomic number is 17, we are just trying to say that it has got 7 electrons in the outermost shell, and these 7 electrons are represented by the 7 dots. Okay, so the number of dots around the element represent the number of valence electrons. This was the foundation for the Lewis-Kosel approach to chemical bonding. And the number of valence electrons help us to calculate the common or the group valence of the element. Okay. So what do I mean by that? Since this has got one electron, this has got one electron, this has got one electron, so all they belong to one family. The same case with beryllium, magnesium and calcium. Since they have got two electrons in the outermost shell, they belong to one common family. The same case with boron and aluminum. In this fashion, this is the way the elements were arranged in the periodic table. And let us try to what you call draw the Lewis structures. Let us take this first example. Since we know that we are talking about the beryllium dichloride. In beryllium dichloride, the central metal atom is the beryllium element, and this beryllium element has got two electrons in the outermost shell. So this two electrons are for beryllium. We also know that chlorine has got 7 electrons in the outermost shell. So these 7 electrons are represented actually in this fashion. Since beryllium has got only 2 electrons and chlorine has got only 7 electrons, so chlorine need to get the stability by 1 electron from beryllium. So this is the way we can write all the 8 electrons for chlorine atom. So the same case with boron. So we know that boron has got 3 dots, that means 3 electrons in the outermost shell, and we have got one electron for hydrogen atom. So boron compound can be represented by in this Lewis dot structure. The same case for methane molecule, which has got 8 electrons around the central atom, that is the carbon atom, 4 coming from the hydrogen and 4 coming from the carbon atom. The same case with ammonia molecule, where I can write the total number of valence electrons as 8, and the 5 electrons are coming from the nitrogen atom and one electron coming from the hydrogen atom. Similar case for water molecule, we have got 8 electrons, total number of valence electrons as 8, 1 coming from the hydrogen and 6 are coming from the oxygen. If at all you carefully look out these structures, they are just trying to represent the octet stability. 8 electron rule, chlorine, carbon atom having 8 electron rule, the nitrogen having 8 electron rule, oxygen having 8 electron rule. And even for HF, we have got the main element, that is fluorine, having the stability by 8 electron rule. So this is what actually the Lewis and Kosel were trying to understand, the chemical bonding for some of the basic compounds. And that's what they have chosen, the central metal atom, and they have placed the remaining atoms symmetrically around the central metal atom, because we can see that whenever we talk about oxygen, okay, that is the central metal atom, and we cannot put 2 hydrogen atoms next to each other. The hydrogen atom should be placed symmetrically. So this was the foundation for the drawing Lewis structures. So we are supposed to choose the central metal atom and place the remaining atom symmetrically around the central metal atom. Whether you talk about water molecule, whether you talk about the methane molecule, where I am just going to symmetrically place the hydrogen atoms around the carbon atom. So this is very important to draw Lewis structures. And we are going to complete the octet of each atom. For hydrogen atom, we are just going to talk about the doublet. So by placing the remaining valence electrons as electron pairs around the atom. So this is the way the primitive chemical compounds were understood by Lewis and Kosel, by drawing dots, and these dots are nothing but the valence electrons. And we have got some limitations with this structures. The rule failed to predict the shape and the relative stability of the molecules. It was trying to talk only about the one term, that is the octet. It never actually talked about the shape of the molecule. It never talked about the stability of the molecule. So this is the one of the important aspect which was not addressed by the Lewis dot structures. Secondly, this rule cannot be applied to those compounds where we have got the central metal atom not having the 8 electron rule. For example, let us talk about the the Lewis acid, that is AlCl3. We know that aluminum has got an atomic number of 13 with a configuration of 2, 8 and 3. So, if at all I try to represent aluminum with the Lewis dot structures, I just have to place 3 electrons in a symmetrical fashion. And I just have to also face 3 chlorine atoms around the central metal atom, that is the aluminum. So, this way I just have to place chlorine around aluminum. So, this is what I have tried to draw all the 7 electrons for chlorine atom. So, here though we tell that chlorine has attained the stability by 8 electron rule, we cannot really explain the stability of the central metal atom, that is aluminum. So, this theory failed for some of the compounds, and it is based on the factor that noble gases are unreactive because they have got the 8 electron rule. But this theory could not actually give a reliable reason why some of the inert gases like xenon and krypton have got compounds in the form of XeF2 and KrF2. Though they were noble gases in which the central metal atom have got 8 electron rule, this theory could not really put a solution why these kind of compounds are still reactive. So, this theory could not actually try to put some light on some of the aspects. So, a new theory was proposed. This theory was called as the valence shell electron pair repulsion theory. This theory is based on the fact that the geometry of the molecule is determined primarily by the repulsion between the electrons associated with the central metal atom. So, if at all I talk about the central metal atom A, and if at all I talk about the atoms attached to it as X, okay, and I've got some lone pairs. So, the geometry of the molecule is based only on the repulsion between the lone pairs or the bond pairs. So, this geometry is just governed by the repulsion between the lone pair as well as the bond pair. So, the limitations of the Lewis theory were overcome by the VSEPR theory regarding the geometry of the molecule. So, this theory was put forward by Cedric Van Poel in the year 1940, and later it was developed by Gillespie and Neuholm. So, we are just supposed to understand that the pair of electrons may be the bonding electrons or the non-bonding electrons. It is these bonding electrons or non-bonding electrons which may give the geometry to the molecule. So, let us try to understand this one. So, there are 3 kinds of repulsion. We can have the lone pair repulsion. We can also have the lone pair bond pair repulsion. We can also have the third category of repulsion, that is the bond pair repulsion, which is the least category of repulsion. And if at all I want to arrange the hierarchy order, I just can say that the lone pair repulsion is greater than the lone pair bond pair, which is greater than bond pair repulsion. To understand this, let us take a simple molecule, that is the water molecule. We know that in water molecule the central metal atom is O, that is the oxygen atom, and we have got 2 hydrogen atoms attached to the central metal atom. The geometry of this water molecule is governed by the electrons, the lone pair electrons as well as the bond pair electrons. So, let us try to find out the number of electrons. 1, 2, 3, 4, 5, 6, 7 and 8. So, we have got 8 electrons, that means 4 pair of electrons. Among these 4 pair of electrons, we have got 2 bonding electrons and 2 other pairs are non-bonding electrons. So we have got 2 lone pair and we have got 2 bond pair. This geometry of bond angle 104.5 is just not governed by only the lone pair or the bond pair. The lone pair repulsion as well as the bond pair repulsion have contributed to the bond angle of 104.5 degrees. So this phenomena is observed for all the compounds. So VSEPR theory was trying to state that it is only the repulsion, okay, the lone pair repulsion or the bond pair repulsion which will govern the geometry of the molecule. And this electron pair and molecular geometry can be easily also understood by the AXEM notation. So this AXE notation will tell you the geometry of many of the molecules. So where is the A is the central metal atom and X is the atoms which are attached to A, and E is the electron pairs, okay, is generally the lone pair of electrons surrounding the central metal atom. And this notation was applied to water molecule, ammonia molecule and many other such molecules which we are going to know in the coming slides. So let us try to talk about the water molecule. In water molecule, the central metal atom being O, and we have got the 2 hydrogen atoms which are bonded to the central metal atom, that is the oxygen. And since we have told that the geometry is governed by the lone pair as well as the bond pair, so I can state that the AX2E2 notation stands for water molecule, where A is the oxygen atom, X2 refers to the 2 hydrogen atoms and E2 refers to the 2 lone pair of electrons. Similarly, for a ammonia molecule, we have got the central metal atom, that is the nitrogen atom, and X refers to the 3 hydrogen atoms which are bonded to the central metal atom, that is nitrogen, and we have got 1 lone pair of electrons on nitrogen atom. So I can state that for a ammonia molecule, the geometry is governed by the lone pair and the bond pair. So we have got 3 bond pair and 1 lone pair. In comparison to water molecules, since it has got 2 lone pair, so the lone pair repulsion has made the bond angle to 104.5. In case of ammonia molecule, the lone pair has interacted with the bond pair and it has brought the bond angle to 107 degrees. So this tells very clearly that the lone pair and the bond pair, they govern the geometry of the molecule. So though this VSEPR theory was able to give the shape for many of the molecules, it has got some limitations. It does not explain the energy of some of the molecules, and for many of the molecules such as ethylene system, where the central metal atom is the carbon and we have got 2 hydrogen atoms attached to carbon atom and we have got another carbon atom attached to carbon atom. So you can see here, though it is an AX3 system, one of the atom which is bonded to the central metal atom, that is A, here the carbon atom is not at all equivalent to other 2 atoms, that is the hydrogen atom. So we cannot really tell that the bond angles are exactly 120 for all the 3 atoms surrounding the central metal atom. Another example is the SOCl2 molecule, that is the thionyl chloride. In thionyl chloride, the central metal atom, that is sulfur, is bonded to 3 atoms, 1 oxygen atom and 2 chlorine atoms. So even though the atoms actually are not at all equal, so we cannot actually tell that they have a ideal geometry as per the AX3E1 notation. So this theory has got some of the limitations which cannot be explained for some of the molecules. So this is the summary of the VSEPR theory. So the VSEPR theory, it states that the electron tends to occupy position, okay, in space where the repulsions are minimum. So whenever we want to say that we are talking about the VSEPR theory, we should talk about the pair of electrons, and these pair of electrons should occupy positions in space that minimize the repulsions. So this is the way we can try to understand the VSEPR theory. Let us come to the next topic, that is the VBT. VBT stands for valence bond theory. And this theory was put forward by Hitler and London in the year 1927 and later developed by Pauling and other co-workers. So it is based on the quantum mechanical approximation called as the perturbation theory. We are not going to in the details of the quantum mechanical calculation, but we should know that these theory is based on the fact that the electrons reside in a quantum mechanical orbitals localized on a individual atoms. And in many cases, the orbitals are designated by simple terms such as s orbital, which is spherical shaped, the p orbitals, which is dumbbell shaped, the d orbitals, which is double, and the f orbital, which are irregular shape. I hope the shape of the orbitals have been covered in the +2 level. So this theory is telling that an orbital on one atom comes to occupy a portion of the same region for another atom. So whenever we are having a bond, we just have to talk about that the orbitals and orbitals, they overlap to make a bond. So the total number of orbitals, the total number of electrons in both the orbitals cannot be more than 2, okay, and the strength of the bond depends on the amount of overlap. More is the overlap, more is the strength of the bond. Less is the overlap, less is the strength of a bond. So this valence bond theory was very clear in stating that the electrons, they reside in the orbitals, and these orbitals, they have to overlap to make a bond. And the electrons are further attracted by the nuclei pulling the atoms together. So we just have to understand by this simple PPT. So this can be understood by the fact that the interaction energy is calculated as a function of internuclear distance. So we have got two atoms, and these two atoms are far away and they cannot have any attraction. When they start approaching each other, so the electron from one atom will have the attraction from the nucleus of the other atom. In similar way, this electron will have the attraction from the nucleus of the other atom. So they start coming to each other. At some point of time, they reach the optimal distance. And when they reach the optimal distance, it cannot further come together, because if at all they come further together, they will face a nuclear repulsion. Because we know that nucleus is basically made up of neutrons and protons. So it is the proton-proton actually repulsion which will come to effect. So this actually VBT theory is based on the interaction energy, and this energy is calculated as a function of the internuclear distance between the two bonding atoms. So these are the two bonding atoms which want to make a bond, and the energy will first keep on decreasing when they come to optimal distance. If at all they further come, they will try to increase the energy, as you can see from the graph. So here we have got two hydrogen atoms, and these two hydrogen atoms have got one electron in the first shell, that is the 1s level, and these electrons, they are present in the orbitals. And what is the shape of the orbitals? As you can see, the shape of the orbitals are spherical in shape, because we told that the electrons reside in a quantum mechanical orbitals, and these orbitals have given the shape of S, P, D and F. Since we are talking about the hydrogen atom, so it has got only one electron, and this one electron is in a spherical orbital. So these spherical orbitals, they start overlapping at some point of time, they merge, and we are trying to get a new bond, and this bond is nothing but a covalent bond, and which is formed by sharing of electrons. This VPT theory also put forward a new concept called as hybridization. What is this hybridization? It is a mathematical procedure in which the atomic orbitals are combined to form a new atomic orbitals called as the hybrid orbitals. So, and these hybrid orbitals are still localized. What do we mean by localized? They are not having a different amount of energy. So, but their shape and energy differ from the standard atomic orbitals. So hybrid orbitals are still localized on individual atoms, but their shape and energy differ from the standard atomic orbitals. Let us try to understand this hybridization concept. We have got one s orbital, one px orbital, py orbital, and this pz orbital. And these four orbitals will intermix to form a four new hybrid orbital. This is the fourth one, this is the third one, the second one, and this is the first one. So you can see here one s orbital and three p orbitals have intermixed to form a new set of orbitals called as hybrid orbitals, and you can see four sp3 hybrid orbitals are formed, and these hybrid orbitals, they have got a geometry of 109.5 degrees. Similarly, whenever we see that one s orbital and two p orbitals, they intermix, they form a new set of orbitals called as sp2 hybrid orbitals. So we have got one sp2 hybrid orbital, the second sp2 hybrid orbital, the third sp2 hybrid orbitals, and these three sp2 orbitals, they immix together, giving a geometry of 120 degrees centigrade. If at all I say that one s orbital and one p orbital, it mixes to form a new hybrid orbital called as sp hybrid orbital. You can see two individual atomic orbitals have formed a two new sp hybrid orbital. This is the first sp hybrid orbital, this is the second sp hybrid orbital. So this is the way we can say that the valence bond theory was clear in stating that the hybrid orbitals are still localized, but their shape and energy differs from the standard atomic orbitals. So we start with a quantum mechanical approximation telling that electrons reside in the orbitals, and whenever we try to make a bond, the orbitals have to overlap, and these overlap will result in the formation of a new bond, that is a covalent bond. And sometimes these orbitals, they start intermixing with other orbitals, giving a new terminology called as hybridization. So the new orbitals which are formed called as the hybrid orbitals, and these hybrid orbitals, they have got a geometry based on the way they try to combine. So we should know that the number of atomic orbitals added together is always equal to the number of the hybrid orbitals formed. So you can see that in sp3 we have got 4 sp3 hybrid orbitals. So if you say that 4 sp3 hybrid orbitals are formed, it is very clear that it is formed from the individual atomic orbitals by s, px, py and pz. The combination of atomic orbitals determines the shape and energy of the hybrid orbitals. So as we told very clearly, it is the hybrid orbitals which combine, giving a geometry and a shape. So it's a tetrahedral shape with a bond angle of 109.5 degrees, and coming to sp2 hybrid orbital, this is a trigonal planar. You can see it's a trigonal planar with a bond angle of 120 degrees centigrade. Similarly, we can say that for a sp hybrid orbitals, it has given a geometry of linear shape with the bond angle of 180 degrees centigrade. So, this is the way the hybridization occurs, and the energy is decreased. So, let us try to summarize the valence bond theory. The valence electrons reside in a quantum mechanical orbitals with having a definite shape. So, s orbital spherical shape, p orbital dumbbell shape, d orbital double dumbbell, and f orbital it is irregular shape. And the chemical bonds result from the overlap of the half filled orbitals with the spin pairing, and the geometry of the overlapping determines the shape of the molecule. So, we have concluded that from Lewis structures where we talk about the octet rule, we have covered the VSEPR theory with the AXN EM notation giving the geometry of the molecule, and we also talked about the hybridization in the valence bond theory. So, the limitations which were laid forward by the Lewis structures regarding the 8 electron rule were overcome by the VSEPR theory, which stated that the shape of the molecule is because of the repulsion of the electrons, and this was further overcome by the valence bonds theory, which told very clear that the shape is not because of the electron pair repulsion, it is because of the overlap of the orbitals, and it was very clear in stating that electrons reside in the quantum mechanical approximation called as orbitals. So, with this I would like to end my lecture. So, if at all actually have got any doubts regarding this topic, the VSEPR theory, the valence bond theory, or the Lewis dot structure, please drop an email or you can just contact my number. Thank you for your patient listening. Thanks one and all.